All right, hi. This is the last set of notes for chapter 3, or unit 3. It's actually chapter 4 of your text. Um, this is like a really short set, and it's kind of like just like catching a whole bunch of details about sampling that don't fit anywhere else. All right, so the first thing here is that when you take samples from the same population, they're going to be like the population, but they're all going to be slightly different, right? So, like when you take a sample, and let's say you take the mean of some measure of that sample, or you like take the proportion of that sample that has a certain characteristic, those means and those characteristics are going to be, or those proportions are going to be close to the mean and the proportion of the actual population, but they're all going to be a little bit off. And all the samples are going to be off a little bit in different ways. So this is what we call sampling variability, right? So if less the population is like extremely homogeneous and has no variability at all, there's going to be some variability there, right? The A note on this is that we tend to believe that the larger the sample is, the more precise that sample will be. So when you measure it, so like if you take a large sample, the the measure that you're taking, whether it be a mean or a proportion or something like that, will be closer to will tend to be closer to the actual population value than the than that of a smaller sample. So big samples are good, and there is a law of diminishing returns on that I've talked about. That like as you increase the sample size, you get more precision. But like when you increase the sample size from like 2 to 10, you're going to get more of a bump in precision than you will be when you're increasing the sample size from like 102 to 112, right? So 102 to 110. So 8 unit jumps, right? So increasing the sample size will always increase precision. Increasing small to small is going to increase precision faster than increasing large to large. I think that makes sense. All right. Statistical significance is something that's like really hard for people to wrap their head around. Um, Typically, when you're doing statistical significance, the idea here is just that the results that you're getting from a study, either an observational study or an experiment, are too unusual to be explained by chance alone. So what we want is we tend to view statistical significance as like, okay, what's the probability that this group has this measure, right? And if I had just taken like any group of random things and measured them, would have I gotten this, right? So like let's say um, I want to know if there's like correlation between being I don't know, let's say correlation between being in ninth grade and having more than uh, 100 Instagram photos, right? So, or let's say being in the upper school and having more than 100 Instagram photos in your thing, right? Is this like something that's unique to that group? Right. So what I do is I say, well, if I had just taken like um, random people from anywhere, right? Um, did this happen because I picked upper school students, or did this happen just because like if I had picked a random group of people in general, then this would have happened anyway, right? So I need a certain reliance that the explanatory variable is actually related to the response variable here, right? And I need to know that that didn't just happen by chance. So this is what we're calling statistical significance. Okay. Um, we'll get into this a little bit more detailed because like right now this is kind of cartoony. Later on, we're gonna like say that like statistical significance is usually measured by something that we call alpha, or which is like is going to be a probability that this occurred by chance, and we want alpha to be, something less than 0.05, right? We would like to have, usually is the benchmark for statistical significance, that the probability that an event occurred by chance, we want it to be like less than a 5% chance of that happening. Now, we're not going to hold that because it's like, okay, what do we mean by unusual enough? And like under most circumstances, having a 5% chance of occurring is unusual enough to be statistically significant. Um, but we might want to hold things to a higher standard in some cases, or possibly like let it off a little bit to hold it to a lower standard. So we're going to deal with that a little bit later, but we're just kind of starting this concept in this unit, and we'll get more specific about that as we roll on. Scope is something that's really important, okay? Like, you have to pay attention to which population your sample comes from. Because if you take a sample from a population, it speaks to that population and only that population. You don't want to say that like your sample speaks to, like if you take a sample of like ninth graders, right? You don't want to say that that speaks to the whole of the upper school, right? Because although a sample of ninth graders is a sample of the upper school, the population from which the sample came was ninth graders. So it's really important to respect the fact that like random sampling, you can only draw inferences about the population from which the individuals in the sample were chosen from. There's a neat one here with assignment, right? If you bring random assignment into an experiment, and the experiment is statistically significant in that it could not, the results of that experiment were not likely caused by chance, then you can make an inference about the connection between the explanatory variable and the response variable, right? So by doing the random assignment, you can start to make a suggestion here that the change in the explanatory variable is actually causing the change in the response variable. Now, you can draw an inference that way. Can you say like for certain that one is causing the other? Well, no. Like you're not proving causation and effect, but you are able to infer that it looks like from the data that this explanatory variable's change is causing the response variable's change, so long as this was done in a well-structured experiment that involved random assignment and that the results were statistically significant. Note, this is different from correlation. Just because two things move together doesn't necessarily mean that one is causing the other. So if you're thinking about an experiment, you have a knob and a needle. I turn the knob, the needle moves, right? That's different from noticing that two needles move at the same time. Two needles moving at the same time is correlation. A knob moving first and then a needle moving in response is an example of causation, okay? And don't confuse these two things. So what you need in order to be even able to draw an inference about cause and effect is that there has to be random assignment in the experiment to begin with. Okay. Last thing here is some quick notes about the basics of data ethics. The big three that are in your text and are also can come up on the AP exam. IRBs, which means that there has to be an independent institutional review board that approves any planned study within an institution. So like a university will have an institutional review board that has to approve all statistical studies done on their students before those studies proceed. That's what we call an IRB. Okay, so that group is charged with protecting the safety and well-being of those students from crazy experimenters. Okay. Two, individuals who are subjects in a study have to be able to give consent. And that's like really, really, really important, okay? That you cannot be studied without your consent. Okay, and that consent can be withdrawn at any point in the study. You can say, look, nope, I'm in the study, I'm withdrawing my consent, I'm out. Okay, so that's a really important thing. So, like, even like here we are in lowly statistics class, consent, 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 consent. Like enthusiastic, positive consent before we move forward, right? All individual data must be kept confidential. Okay, so IRBs, consent, and there should be a reasonable expectation by the participants in the study that you are not sharing their data as in terms of personally identifiable information. Okay, that generally speaking, the ethics say that if you're sharing people's data, you should be sharing it in the aggregate, meaning that you're sharing it as like, ooh, this group of subjects manifested this response, not this person did this. Okay, so you can release data in the aggregate. You cannot release it on the individual level because people have a right to their own information. So the buying and selling of personally identifiable information as far as the AP exam is concerned is no. Okay? Unless you have given consent for somebody to release your confidential information, it should not be shared. Now, how often are you actually giving that consent? That's a whole nother matter. Like when you sign an end user licensing agreement with Facebook, did you give Facebook information, like the ability to go and give your data to somebody else? I don't know. You have to go read that end user licensing agreement, right? So these are important things. You probably did not read that agreement. I would advise that you do, and if you have an extra couple hours in your life to find out what you actually told Facebook or Twitter or Instagram or whatever that they're allowed to do with your stuff that you're putting into their machine, right? So big three for data ethics: institutional review boards, informed consent, and confidentiality. Those three, it's like just kind of like keep those in the back of your head. All right, so we'll talk a little bit about more of this because this is some of the yicky, like less firm stuff, but this is the last section in this unit. We'll spend a couple days on this in class, and then we'll go from there. Thank you.